abanye bahleli in groups lapho.
Abanye se bebecela ukuthi ubarekhodele bapostele bandla ku Blackboard mungakwazi.
I will record, Val, I will record.
Duncan, thank you.
Yeah. I just request that you do not interfere with the recording, guys, when we started. There's one document that I had to open.
Susumubi wakho wena lethu lapho. Yini manje?
Okay, guys, let us start. Lethuktula, thank you for showing yourself. Okay, guys, I will switch off the camera. Then I will start the recording. Let me start by switching off the camera. It takes a lot of bandwidth. I will request that, guys, if anybody has a question, there is a hand there that you raise, but when I'm presenting, I cannot see the hand. Okay? So I allow you that if you want to ask something as we continue with the discussion, just feel free to interrupt and say whatever you want to say, then switch off your mic. I request that we keep our mics switched off so that we do not get disturbed. Okay, now I will start the recording, then we will start the lesson formally. Nolas, you can switch off your camera now. Okay, good people, good evening, and welcome to our online class tonight. This session is being recorded. We will start the session formally. I will start by showing you the documents that were given to you and the documents that you are supposed to download from Blackboard. Then we'll go into the content. I'll start by sharing the book with you. Okay, I'm sharing the book now. Good people, this is the book that is prescribed for you. We requested you guys to download this book so that you can be able to read the references that we make to it. It's a PIC microcontrollers and embedded systems. You know the title. I just want to draw your attention to what we have done. As I said in the beginning, we are not going to read the book and the notes and all the data sheets together with you. We will explain the principle and expect you to go and read. Like this section 2 is the architecture and assembly language. I just want to show you that if you go to section 2 here, they explain the basics that we have discussed. Like if this 2.4 is the status register, 2.8 is the program counter and the stack that we just touched on. But I want to draw your attention to this. This is where the status register is explained in the book. They explain everything that you need to know. Then they give the description of each bit now in the status register. I will expect you guys to read this so that you understand the status register in detail. Then below that, they give you examples of how these bits can be affected if you run your program. Well, the addition here is the same irrespective of the language, but the instruction here is a assembly language. In this section, up to section 7, all the examples are in assembly language, but everything that is done here, we can be able to do in C. For our start, we are interested in C. Then, good people, I will unshare this. I will unshare the book, and then I want to share the data sheet now. Okay, let's look at the data sheet. I'm sharing the data sheet now. Okay, here is the data sheet. So sorry, I'll minimize the size. I will zoom it up to. But anyway, you have the data sheet, guys. So I just wanted to show you that, like here is a stack. It goes together with the program counter, but I want to go to the beginning. This is the data sheet is written by Microchip, who is the manufacturer of our device. So here you can see here it says pick 18FXX8. So there can be any two numbers here that end with the 8 in this family that we are discussing. So there is 28 pin and 40 pin. For us, we are discussing the Then I gave you guys these notes. Let me show you the notes. I'll just show you the documents before we get started. I will unshare the data sheet. Then I want to share the notes now. I know you already have these notes, but I want to show you what it is like. So these are the notes that were given to you, people. And you should be having them. So then when we do our lessons, we'll refer to these documents. You should all be having this as a soft copy. But if you like, you can print for yourself. This document is a document that carries almost everything that we are doing. Eh? Is this the right one? Eh? Yeah, that is the right one, but not the edited one. Then, guys, having shown you that, I want us to start by looking at lesson 1. We are not going to do the lesson as such, but we'll just go over it and show you what was discussed and what you are expected to know. So we'll go through all the 4 lessons, then summarize here and there, then go to important discussion. Then I will expect you to tell me if there's anything that you'd like me to explain further or something that you have problems with. Then we talk about the test. This is the lesson 1 that we covered with you. Guys, I want to believe that you can see this screen. Eh? Can we all see the screen?
Yes.
Yes, sir.
So here is lesson 1, Introduction to Microcontrollers and C language programming. Before, guys, I requested that before you come to class, you must read these references and look at what is given to you so that you can be able to follow when we try to explain. So here it says, read from page 2 to page 11 in the notes. So I just want us guys to go and look at this page 2 to page 11 in the notes. We will come back to our lesson, but we will not read line by line or sentence by sentence. I just want to show you what you were supposed to learn from there and explain the basics. So this is our document. So then it says, say, read from page 2. This is page 2. This is introduction to C programming. Here I said embedded C programming. If you read this, you'll find that the C that we use here is slightly lower than the C that you use for the microprocessor and other high-level programming languages. So we started with a brief history of when was C developed. You don't need to know these details, guys. This information was for your enrichment. What I want you to know is that the language features are portable. This means that you can write a program in one microcontroller or for one microcontroller, and then you go and run it in a different microcontroller. That is what we mean by portability. But we say now the processor-specific libraries are not portable. That means you can write the program general information, but that include file which applies specifically to a particular microcontroller will not be taken to a different microcontroller. That's why we mean if you say it's not portable here. Then we say the processor-specific code, like the interrupts and all that, are also not portable. So when you take a program and want to run it on a different microcontroller, you must be able to edit it so that you can add that information. Here, guys, I will show you in the book, but here we say C is not as efficient as assembly language. Our book in section 7, before we continue with our notes, we'll go and look at the section 7 where C language is introduced. Then here we wrote that a good assembly programmer can do better than the compiler. So I also believe that if you are good in assembly language, you can do better, although we say C is easier than assembly. So that was on page 2. Then you need to just have an idea of this diagram. You don't need to know the details. That's why I just gave you to read this section and did not touch it in class as a lesson. This is an overview of how the compiler handles your program. We write the program with the .c. That .c means we're writing in C language and we are writing for the compiler. But all this is what takes place inside the microcontroller. Also, we can do what is called the modular programming, where if we write a complex program, I can write a certain section and one write another section at a different area and the other one write another section. Then we can generate different object files and link them to produce one hex file. That is a function of a linker. So for our application, we want to go into detail with this, just that at the end, when everything is done, we produce the hex file. That is what we load onto the microcontroller, we pen into the microcontroller. There is also a map file that is produced. This map file shows you how the program is arranged in memory and how much memory is used. So this COF works with the error file. Is what produces error for you when we're writing the program. We write the program, when we compile it, then it generates the errors at the bottom. Those errors are contained in this COF file. It goes together with the error file. But we want to go deeper into detail with this, guys. It's just an overview. Okay. Then next, the C runtime environment. Guys, this is what happens inside the microcontroller when you run the program that is written in C language. So the compiler will set up the runtime environment. It will allocate the space in memory that will be used for stack. In assembly language, we use the program counter in the stack. But in C, it generates an artificial space in memory for the stack. Then it will initiate the stack pointer. All this is a theory that you need to know this just to have an overview of what takes place inside. But we write the program by calling the main function. So we therefore look at the fundamentals of C. Guys, this is generally a high-level C language, not the ANSI C or the one for the microcontroller. But the basics is the same. We need to have a header file. This is standard input-output file. We need this file if we are going to display something on the screen, like on the laptop or the computer. It's a standard input-output file. Here, I showed you this in our last class where we're defining the pin. We said in this example, we say in a program, if we write pi, the microcontroller must substitute 3.14159, which is the value for pi. If you look at this example code, people here, it says that this then will send an output of in type int, but it will receive no input. Is an example of a program that sends the output out from the main. So here we declare these data types. Again, these are the general data types. For us, we don't use float, we use long instead of this. So here, in this area, calculate the radius. Then it will return, that return into there will be the area. This print file instruction sends out the output. That is what will go out there as the output, the area of the circle in this example. But we want to go into detail with that. So, and the data types we have discussed. Then we discussed the comments and all that. So this is information that we wanted you guys to go through and you do this tutorial and this introduction to Mplab X. Previously, we were using Mplab. We started with version 6 up to version 8. Then we jumped to Mplab X, which is version 10. This theory, you need just to know where we come from and how things have evolved up to then. So for us, then we don't need all this information. It's just for your enrichment. This is the old type of Mplab. This is how it was. It's a window, or the GUI, we will say the graphical user interface. Then the IDE, the Mplab X IDE. This is the first version of Mplab X IDE that came out, 3.5. That I captured is 3.5, but we started with 3.47. Okay. This, Mr. Mngomezulu, has discussed with you in the lab. We'll tell you when you need it for test purposes. This section, guys, we use that at the beginning when we introduced Mplab X, we're still running Mplab 8. So we have to switch the drivers. We need to tell now the drivers whether you are using Mplab X or you are using Mplab 8 so that they provide the correct tools. But we don't need this anymore because we're only running Mplab X now. We are not running both. So this information, guys, is what we are supposed to go through before we get to our lesson. Our lesson starts here then with the architecture. I was just going over this. Then I want us to go back to our lesson and see what we were supposed to do. Let me share lesson 1 again. So if you look at this now, that means you are supposed to go over that material that we have just highlighted before we do today's work, or the work that was done on that day. So here, guys, I gave you an example of a smaller microcontroller. Guys, if you design, you do not necessarily have to use the PIC18 F458. That you speak is a 40 pin. If in your design you need 5 or 10 pins, then it will be a waste to go for that big end microcontroller. You can still use the smaller one. That's why I put this one. You can apply the knowledge that we teach you there on this one. You just need to know how to handle it. So, but this was just for explanatory purposes. We are not going to use it. And this is our microcontroller. Guys, there is so much that we need to learn on this microcontroller. We want to do everything in one day or in each lesson. So we explained the master clear, and previously we looked at these port pins. They are multiplexed, like port A is multiplexed with the analog. Port A and the port E also has got the analog. So there are 7 analog channels running from AN0 up to AN7 here. And we also spoke about port D that has got the capture and compare. Here the CCP. And we said we need to be able to switch this. The other functions are not critical. We can use them anytime. We'll learn them as we go along. So this diagram, guys, is very important for you. You can take a snapshot for this one and keep it in your phone. You will be allowed in the lab, if you do the break or anything, to quickly open that so that you can see which pins you are connecting to. Okay. Then I gave you a quick explanation here. Then we looked at this example of a schematic. Guys, if you want to test a program in Proteus, please use what we call the active animated LED with the colored one so that you can see it turning on and off. But the aim of showing you this diagram, good people, was to show you that if we are required to design or develop a system, it can be a test, it can be assignment, it can be an examination. We do not expect you to write inside the rectangle here that represents the microcontroller. Although in the diagram here, if you look in this diagram, they do indicate the pins inside the pin numbers. But for us, when we design, we don't write anything inside. Another thing that I can point to you here before we continue is that we spoke of VDD, pin 11 and pin 32. The VDD, that where we connect our 5-volt supply, and VSS pin 12 and the pin 31 where we connect the ground. So we connect the power on the left-hand side and connect power on the right-hand side. If you guys build the circuit, you have to connect all of these pins to power. Do not connect only one side. You may have problems. Okay, so we're saying then that inside the microcontroller, we only indicate the master clear pin and the code. But make sure that we only, another thing, we only show the pins that you are going to use. If you need only one pin as an output, you only use one pin. If you need one pin as an input, you use one pin. If you need only or 8 pins, you can put 8 pins. But we are not expected to show all 40 pins here that are in our microcontroller, or the 33 pins that are input and output. Another thing is that we connect the power, as we've spoke about VTT and VSS. We know that for your circuit to operate, you need to connect power. So we do not show it power. We do not show the power in the design here. But when you now build the board, or either the breadboard or the PCB, whatever, then you need to show your power connection. Also, the microcontroller is a digital device. We need the clock source. We do not also connect the oscillator. We know that for it to operate, you have to connect the oscillator, but it did not show its connection here. Do you get that, good people? Then make sure that you label all the pins. And we said we'll use 470 ohm resistor. Please label all the resistors. The LEDs, if you are not going to use LED1, LED2, or whatever, you may leave it unlabeled. But if you've got sufficient space, then you can label them. Let us look at a simple program that you can run on this, then I will show you something. This is an example of a C language program. We said we use the include file, and this instruction, we said this tells us to add this header file. That .h means this is a header file, a file that tells us about our microcontroller, controls the library information. It has all the registers that are used in microcontroller and their addresses and the other library information that is required. Then we said we run the main program. If we say void main void, we mean there is no output and there's no input. Everything takes place inside the microcontroller, and it runs now between these two brackets. So this is where everything will be taking place. And we said if we write an instruction like this, good people, I hope you can see here. If we write an instruction like this, we are telling the microcontroller to reserve a space in memory, an 8-bit space. Car is 8-bit. But if you say unsigned, we mean that you want to hold positive numbers between 0 and 255. Then it will call this space Z. Just like we have discussed the registers, guys. The registers have got names. Those we call the specific function registers, SFRs. Like the port register, that is where the pins are connected. The trace register, that is where we make pins input and output. Then we have got registers that can be used at any time for any function, and we call them general purpose registers. So if we write an instruction like this, we are telling the microcontroller to reserve a general purpose register inside and call it Z. So in our program, if we refer to Z, then we will be referring to the value in that microcontroller, or sorry, in that register. Or we will be either putting a value in that register, incrementing a value in that register, or reading a value in that register, depending on what we want to do. But this is how we declare a general purpose register. We use this variable Z now to represent a register inside the microcontroller. We said a trace is a register that makes pins input and output. If we put a 0, we are making a pin and output. If we put a 1, we are making a pin and input. And we can work with 1 bit, or we can work with any combination of bits, or we work with the whole register. In this example, we put zeros in all the bits of trace B. Thereby, we are making our port B an output. Then we introduce this for loop to you. The for loop, guys, basically is used for counting purposes or for tracking, or we call it, if we don't want to call it tracking, we call it an indicator or a pointer. So with this example of the for loop here, we said there are 3 things taking place in the for loop. Is this one, and that, but there is a sequence. You do what is on the left, then come out and do what comes below, then increment on the right, then test. We need to have that while one at the bottom, that while one is terminated. It tells the microcontroller that if the result of this test here is true, it must continue to execute what is below here. But if that result is not true, it must come out of the loop. Again, guys, something that I did not tell you is that you can perform more than one instruction in the for loop. If you are to perform more than one function, then you need to put brackets here below the for loop and put all your instructions. But if it's only one action, then we do not need the bracket, so it's okay like this.
Sir.
Guys, is there anybody that has any question before I demonstrated this program and that task to you?
Yes, sir.
Yes.
Sir, would you please re-explain that line that is highlighted, unsigned car?
Or this line?
Yes, and while one.
Okay, thank you.
Thank
Good people, please, if you have a question, don't keep it to yourself. The aim here is to polish up what we already know and fill in the gaps here and there. I'm saying to you, in the microcontroller, we have got this. This is our microcontroller, and we said this instruction tells the microcontroller to add this file to our program. This file has the library for all the registers that we have in the microcontroller. We have registers that perform specific functions like a trace and port. In this example, we are using trace B and port B. Port B is where the pins are connected. There are 8 pins connecting here for port B, as indicated in our diagram here. And we use then trace B now to make these pins input and output. In this example, we put 0 in trace B, we make all pins output. But inside the microcontroller, the memory structure for our microcontroller is slightly complex, but we will look at something before the end of this presentation. There are registers that perform specific functions, like the port, the trace, the status, and the others. Then we've got another lot of registers that can be used for any other purpose. You just need to tell the microcontroller that I want to use that register and use it for that purpose. My advice to you is that you must give it a name that is related to what you are going to use it for. Especially in assembly language, we maneuver that, we manipulate and control that. But in C language, we use a compiler. Then it's like that we wanted to keep on displaying value, but we wanted to be able to keep track of which value we have displayed to see whether we have displayed all or we still have to display something. Therefore, we take one of the general purpose registers. This line here, if you say, in other words, here we are requesting the microcontroller to reserve a register. We are dealing with 8-bit system. So with this line, we ask the microcontroller to reserve a register. And we tell it that in register, we are going to store positive numbers. If we say unsigned car, we mean positive numbers between 0 and 255. And we say it must call this register or this memory space Z. You say here unsigned car Z, but it must reserve a register or an 8-bit space and call it Z. So in our program, when we write trace B, the compiler will check in this file here and find the trace B. When you write a port B, it will check in this file here and find the port B. We cannot just go and write Z without telling it. So if we say unsigned car Z, inside the memory, the microcontroller will go and pick up a register at a certain address and call it Z, so that when we write Z here, it will refer to that register. So we use a line like this then to declare a general purpose register in the microcontroller. In short, we simply call it, we're declaring a variable, but that variable is a register inside. I don't know whether you get the picture of what I'm trying to explain. Do you get that, good people?
Yes, sir. Yes.
Okay.
So
Now
it's the one.
this is what we are doing. This register is 8-bit. That car said 8-bit. It means it can count from 0 to 255. We can keep on adding 1, 1, 1 on it until we reach 255. So let's see what we are doing now in this for loop. We started by putting 0 in Z. After putting 0 in Z, we said this equal sign is not equal to, but assign. We say assign 0 to Z. Then here now, we come to this line with a 0 on Z. This instruction says assign what is on Z to port B. So we take 0 from Z, we put it in port B. So we put this now on port B here. So there'll be 0, 0, 0, 0, 0 here. Then no LED will turn on. Then after doing that, we come and add 1 here on Z. This is Z++ means increment, we add 1. So we come here and test. Now when we test, we have got 1 in Z. We ask, is this 1 less than or equal to 255? Is that true? Yes, it's true. Because of this, while 1 will come out here. When we get here now, there is 1 in Z. We take that 1 in Z, we put it in port B, and so on and so on. That will keep on happening. Now, good people, I wanted to open this in Proteus and demonstrate it to you, but I want to ask if anybody has any question before we go to Proteus.
Yes, sir.
Yes?
Sir, you said if Z is equal to 0, the light will not turn on.
Now, let us look at our circuit. These are our LEDs. Guys, please make sure you understand the symbols that we are using. If we write this symbol for the LED, this side represents the cathode, and this side represents the anode. You should bring in your electronics 1 technology or skill. In electronics 1, we said we use P-type and the N-type semiconductor material. And also in digits 1, we discuss that. So this represents the N-type material. The N-type is full of negative charges. The negative charges we call cations. Then the pin that connects to the cations we call the cathode. And the P-type material is full of positive charges or holes. The positive charges we call anions. And the lead that connects to the anions, we call it the anode. So if we connect a diode like this, then the cathode must connect to negative and the anode must connect to positive for the diode to forward bias. If then that diode is an LED, when current flows across the junction, is going to emit light. So you must understand the meaning of the symbol. And always make sure that you connect this side to ground and you connect this side to positive, or we'll send positive on this side. Now, we have the 0. Our ground represents 0. We've got a 0 on all these cathodes. Then if we put 0 in port B, there is 0, 0, 0, 0 here. We've got a 0 on the anode and 0 on the cathode. The diode then will not turn on. So that's why then I'm saying that if in this line we put 0 in Z and take that 0, put it on port B, all the LEDs will turn off. Do you get that, good people? Are we okay with that?
Yes.
Okay. Please talk, good people, so that we can see whether to move on or to explain something else. Now we come with a 1 on Z. We take that 1, we put on port B. 1 is the LSB. So this bit now, RB0 will be 1. All the others will be off. So this one will turn 1. Guys, look, as this is here, the MSB is at the bottom, the LSB is at the top. So that one will turn on its 1, all the others are. In other words, we read from bottom to top. It will be 0, 0, 0, 0, 0, 0, 0, 1. then that will turn on. Yes. Yes, khuluma miss.
Ngiyacophoza ukuthi iphaleni ena i-trace register ukuze kukhanye ama-LED sifake o-0 angithi.
Yeah, for the LED to turn on like this, we must make it an output. To make the bit an output, then we put a 0 on trace. Because we are using all the pins, then we must put a 0 in all bits of trace. Yes, miss.
While sekonje sifaka mase siqede i-program i-code yethu ubhala i-program yethu sifaka while.
Now, guys, please listen carefully. Listen carefully. This is what we are doing. We will do this, do that, increment and test. If we put while 1 at the bottom here, we mean that if the result of the test there is true, we must keep on doing what is below here. But if the result of the test is not true, we must come out of the loop. That is what this while means. It's different from the while that we'll discuss in the near future just now. But this while that we put here, it says while 1 says, if the result of the test is true there, we must continue executing the instruction below the loop. Okay, thank you for the questions that you guys are asking. Let us go to Proteus and have a second like this and run this program and see what will happen. So allow me then to unshare this. Then I will open Proteus. Let me share Proteus here now. I hope you'll be able to see it. Okay, can we all see this Proteus schematic on the screen?
Yes.
Okay, let's first look at the program, good people. This is the program that we just discussed. Now, guys, this will still tell you about this, but we will explain everything as we go along. If we run a program in Proteus, it's the same as when we run it on the microcontroller. So we need to set up the hardware that we call the hardware configuration. If you test in Proteus, it will run, but for other purposes, you need to maybe to switch off the overflow, the stack overflow and all that. So we set up the configuration bits. We are still going to discuss the configuration register with you. There is a register inside the microcontroller that helps the microcontroller communicate with the hardware devices that you connect out from outside the microcontroller. So we use this directive now, pragma config, in C language to show that we are setting up the hardware. OSC is the oscillator. XT is 4 megahertz. There are 4 types of oscillators that we work with. XT is 4 megahertz. Anything above 4 megahertz we call HS. And anything below 4 megahertz we call LP. Then we have the RC oscillator. The same RC oscillator that you use in 555 timer. I want to believe that you guys did start the 555 timer somewhere in S1 and S2. Then you need to switch on the power up timer. We'll discuss in detail in the near future what the power up timer is used for. This is a brownout reset. We switch that one off. Guys, the brownout reset, you might have noticed either in the rest or in class, sometimes we have power dip where the lights will dim, not switch off, dim and come back on. That is what we call the brownout, the power dip. So if the voltage on the microcontroller can drop from 5 volts to any value below a particular value, it can switch off. So this prevents that from happening. Then we've got the watchdog timer. The watchdog timer, guys, in the microcontroller checks if the program is running. If the program stops for some time, then this is part of what is used for power saving. If you're not touching the buttons on your cell phone, after some time the screen switches off, so the watchdog timer kicks in. And also, if your program can hang for some reason, hanging on one line and not be able to continue, then the watchdog timer will kick in. So to be on the safe side, then guys, we switch off the watchdog timer for our experience. This is the stack overflow. It's one feature that you'll notice sometime if you run a program in the microcontroller in Proteus, it keeps on hanging. It maybe count up to 7 and then start from the beginning. It's because of this stack overflow control bit, then it's advisable to switch it off. We did talk about the sensors that are put all over the field. It takes a long time to go and service those sensors. Our micro supports low voltage, that is 3.3 volts. You can run it from the small battery, the same as one that is used in watches and in calculators. So to show that we wanted to work with VTT, so we switch off this LVP. These guys will be discussed in detail with you in the future when you need to work about it. For now, I just put it on so that it does not affect our program. So this is the program that we have just discussed with you guys. Another thing that you must notice is that the compiler puts colors to represent the different data types and different values, as you can see here. So I want us to run this program now in our microcontroller. I just copied the program from the lesson and put it on here as it is. Let us run the schematic, guys. Please watch this. So this is the LSB on the right and the MSB on the left, the way I connected. Just check what is happening. We keep on adding 1. We are counting in binary. Another thing that I want you guys to observe as we are doing this is that we use a red to represent 1 and blue to represent 0. As you see here, 1 is red, blue is 0. Again here, where there is blue, the LED is off. Just look there, guys. We keep on adding 1. We are counting in binary. Yeah? I hope you can tell me what count is that now. Just check and say, I reduced the speed here so that we can be able to see everything happening. Otherwise, it could happen very fast. I'm running. Sorry, I keep on adding 1, just like you saw the program there. That's the program that we are running. Look what is happening, good people.
Sorry, sir.
Yes.
Sorry, sir.
Yes.
So before uqhubeka kakhulu, bengicela ungitshele mina la angiboni kahle ukuthi ngophi lo one omeda ngephi la item akwenze njani. Angiboni kahle.
But do you see what is happening on the lights here?
Yeah, I can see that.
So you see we're counting from the LSB is on the right here. So we keep on adding 1 here and add to that and keep on adding to that. So like right now, the number is 110110. Look there. Look. So this is the LSB. Eh? We keep on adding 1 on the LSB. Now look is 4, 5, 6, 7, 8, 9, 10. I'm talking about the LSB side. Can you see that? This is LSB. Is 2, 3, 4, 5, 6, 7, 8. Then you keep on adding on that. Yes, there's another question coming in.
Oh, all right.
Somebody wanted to say something also. Look, guys, we keep on adding 1 here. We're counting from here, then adding on the MSP all the ways, incrementing all the time. So, sorry, sir. Yes, right now we've got 1. Yes.
Sorry, sir.
Pick up.
I wanted to ask if
before you ask, check what will happen, guys, when all LEDs are on there. We are about to get to that point now. Check. Then I'll give you a chance to ask a question. What's happening? you see now it's now what is that is 110. That is the E. So on the MSB is now F, the upper nibble. Can you see that is F? The upper nibble is F. We keep on incrementing the lower nibble. Sorry guys, I paused that. I thought it was going to show us. See, did you see when it comes, when all one is start afresh? Okay, it's counting now. So it's incrementing on the LSB. That is C, D, F, and so on. It keeps on adding 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Then you keep on incrementing there. But this is how we count in a binary. Guys, I thought it was going to be possible when I pause it that it displays the values, but when I pause it, it kicks out of this. But did you see what this program is doing, guys? We're counting from the, we started by putting 0 in Z. When 0 is only RB 0 that comes on this one. Then we keep on adding 1, it becomes 1, 0. Add 1, it's 1, 1, and so on. Let me run it again, guys. Please observe carefully. It's now start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 0, 1, 1, 11, 12, and so on. Can you see that we are counting in binary? Any question on this schematic, guys, and this operation of that program? This is what we covered in lesson 1. Yes?
Sir.
Yes, Koloma. I see there's a hand up, guys. I said, do not worry about raising the hand. When I'm presenting, I cannot see the hand coming on. Feel free to speak.
Sir.
Yes, TP.
We have to know the config part, or we have to know it for lab purposes.
No, that configuration at this point in time, guys, is not for test purposes. I just put it on there so that we won't have a problem doing the demonstration. But for test purposes, guys, we won't be tested on anything that we have not covered in detail in our lesson. Any other comment?
Sorry, sir.
Yes, Zulu.
Ukuze sir ukuthi kwi-test le sizoyibhala sizobe like sinikeza instruction kuthiwa asidizayine lamakhodi layo kade siwadizayine eklasini, or noma sobe sibuzwa imibuzo mhlawumbe ukuthi si-understand yini ukuthi uma ufaka u-trace B ku-0 kwenzakalani, ukuthi angi-understand ukuthi ama-question aphuma kanjani.
Just allow me to finish this. We're about to wrap up on this, guys. Allow me to wrap up on this. And then I said I'll give you the guidelines on the test. After that, then you can ask that question. Okay? We will go over that. Okay, guys, allow me to unshare this then, or even before we unshare this, good people. We, at the end of lesson 1, we said we want you to write a program that turns on all the LEDs. So what do we do now? Let us just cover all that here while we have this demonstration. So for us here, guys, it means if we want to turn on all the LEDs, we need to take out this for loop. Yeah. And we said if we want to turn all, we put 1, 1, 1, 1, and it has a small 0x FF. Let us see what can happen if we run this program. Guys, always note we've got that button here that is 010 at the top. We use that to build the project. To build the project means to convert it to hexadecimal. In other words, is to put in action that diagram that I showed you in the beginning, that was having the compiler, the linker script, the map file, and so on. With that tool, will engage that. If it says build successful, it means there are no errors. It does not mean that the program is correct. It only means that there are no errors. Then let us run this and see what happens now. So you see what is happening now, guys. We just changed one line. Can you see that? Are you guys still with me?
Yes.
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 So,
So,
look what we did here. This is our program. I took out the for loop and then put 0xff.
Okay, ngiyakubona lokho sengichazela ngo-line 16 sir.
Line 16. Guys, this line 16, I explained that in class. There is another one that I did not put. This line 16, if let's go back here to the schematic. Look at this schematic, guys, the diagram here. If you look at port D, we've got RD0, RD1, RD2, and so on. But if you look at RD4, it's got CCP, and there are others that got the PSP and so on. That is the comparator. I was explaining that to you when we were doing lesson 4 in the class, and we explained that also in the lab. Now, when I wrote this program there, I did not know on which port I was going to run it, but I always try to stay away from port A unless I have to. So if you are going to use port A, you must switch off the analog to digital converter, this AN bit, so that they function as digital. If you are going to use port D, you must switch off the comparator. So this line then, guys, not for test and exam purposes, but for practical purposes, you must always have that line on there. There we are switching off the comparator. I will show you that if we remember before the end of the lesson, we can look at the data sheet and look at the comparator. So here, guys, then we put FF to 10 on all the LEDs. Let's see what happens if we say 0F. Let's change there and say 0F. Each time you change something on the program, you must compile. When it says build successfully, then you come and run it. Look what happens now. We put 0F. Can you see now that the upper nibble is off, the lower nibble is on?
Sir, they are all off.
Yes. Sorry?
They are all off this side.
Nothing is
Look,
on.
oh, now it's on. Yes, sir. It's good now.
The upper level.
Yeah, so the lower nibble is on. Look, we've got ones on RP0, RP1, RP2, and RP3. That's the lower nibble. Can we all see that now, guys?
Yes.
Okay, then let us go back to the program now. And let us change and put F on the, guys, again here, this F can be small letters, can be capital letters, it doesn't matter. Now we've got F0. Let us compile that. Then let us see what happens. See what happens now. The upper nibble is on, the lower nibble is off. Can you see?
Yes.
Can we see?
Yes, we see, sir.
Yes.
Yeah. Then, guys, we also, although we do not have a what you call a delay, Let us see what happens when we put CC. We spoke of CC. Let's see what happens when we put CC on there. Do you see now? 2 are on, 2 are off, 2 are on, 2 are off. Eh?
Sorry, sir.
Yes.
Screen says see balekile la.
Do you all have that problem, guys? Nothing has happened on this side? Yes, what?
Screen.
Okay, let me share it again, good people. It's okay. Okay, can we see it now?
Yes.
Yes. No.
Can you see the screen now?
Yes. Yes.
Okay.
Yes, sir.
I put CC there now, and the 2 are on, 2 are off. Let us see what happens if we put it 3-3. We said CC 3-3. Let us put it 3-3 here and see what happens now.
The bits will alternate.
Okay, I hope the screen is still on. Okay, do you see now those that were on are off, those that were off are on? Eh? If you could have a delay between these two actions, then they're going to toggle. Guys, is there anything else that you want me to explain on this? I want to go and talk about the switch, then we talk about the exam. Is there anything about the test? Is there anything that you still want me to explain in this? We have covered almost everything. I just want to go and demonstrate the one with the switch and then talk about the exam. Tell me about the test. Okay. Okay. Okay, guys, let me unshare this Proteus now. I will go and share lesson 4. I'm sharing lesson 4 now, good people. I hope we can all see lesson 4. Again, guys, if you have a question, do not worry about raising the hand. I won't see it. So here in lesson 4, we spoke about inputs and outputs. We have discussed this in class and I've given you the theory that you need. I just want us to talk about this schematic. So here we have a switch connected to RA0. Then we've got a motor connected to RC7. We've got an LED connected to RD2. Guys, here, please, good people, take note. If you were doing design, just for tests and what is not a problem. But if you're doing a design or you are going to build the real circuit, make sure that it's a 5 volts motor so that it can be driven by the 5 volts from the microcontroller. Otherwise, there will be a problem. Then we said we have got this 10K that connects to the master clear so that our program can run. And we said the switch now, when we connect a switch to the microcontroller, a switch is an input. It can be a switch, it can be a sensor, or anything that is an input. You need to know the condition at all time, except if it is analog input, then you need to know the minimum and maximum and the scale your signal. We will discuss that in future lessons. So in a connection like this, we've got this 10K resistor such that when the switch is open, we said we use a button type switch, which is spring loaded. When we press the switch, it will close. When you release it, it will open. So when the switch is open like this, we have a 1 sitting on the pin. When we close the switch, yes.
Khona la kade sewushintsha lapha ku-port ushintsha ufaka o0
FF sacela ukubuza ukuthi lapha ku-trace bewushintsha yini nakhona because ekuqaleni uthe yena ku-trace sifaka u-0 if kumele ama-LEDs ethu akhanye wonke.
Yeah, a trace is for making pins inputs and outputs. After you have made your pins outputs, then you do not touch the trace. You only send something on the port. Your pin is already output. You play with the values on the port because the trace is for making the pins outputs that you do once. If you make your pin input, you do it once. So you don't keep on changing or making it an input or output, or to make it an output all the time. Once you have made the pin the output, you have finished, then you can use that pin until we have finished what you are doing. So we set up with the trace once in a program. Thereafter, then we play with our output. If we put zeros in trace, we are making all bits outputs. So we can put anything on the port now, safely so, knowing that the pins are already output. Unless if you want to change and make the pin the input, then you can go to your trace again. But if you are going to use your pins as outputs, once you set your trace to make your pins outputs, you don't interfere with it again. Says one.
Thank you, sir.
Yes, sir.
Okay. Then here now, we've got this resistor putting a 1 here. If we close the switch, there will be no resistance between ground and the pin, so there will be a 0 on the pin. We say, therefore, that this resistor is a pull-up resistor. It pulls the pin to logic level 1. In this setup, guys, the instruction, if we look at the instruction at the top, there must have been an instruction here. We don't just write a program. The instruction says, develop a digital system interfacing a switch, a DC motor, and an LED to a microcontroller. We said the word interface means connecting external components to a microcontroller. So we want to connect a switch, a DC motor, and an LED. Then we say, when the system is idle, you must get used to these terms, guys. That means when nothing is happening, the LED is on. But when the switch is pressed, the motor runs. This is just for demonstration purposes, guys. You won't find something like this in the field. Then we go to our program. Look at the program now, guys. We won't worry about the first part, that is the comments. We said we need to have that. Let's look at the program. This line we already know. Here we are defining this. We said we'll use this define directive to tell the microcontroller that if it sees the SW, you must know that we are talking about this pin, port A bits.RA0. Instead of writing port A bits.RA0, we just write SW. And instead of writing port C bits.RCW, I just write MOT, which is abbreviation for motor. And instead of writing port D bits.RD2, we just write LED1. Then the configuration here is because we want to test this program in a hardware. Then this is our program now. Void, main void, you have seen that. Say no output, no input. Now, I've got this line, guys, because if we look at our schematic, we have the switch connected to RA0. We checked that port A multiplex with the analog inputs. So this instruction now switches off the analog to digital converter. Is setting up all the pins with the AN as digital input-output pins. Again, we will use port D, so I switch off the comparator. So these two lines, guys, we are not going to lose marks if you don't have them in the test and in the examination. But if you do not have these lines in the design or in Proteus when we do the assessment, your circuit may not work. So it's always advisable to have these two lines in your circuit, guys. Just normalize doing that. Make yourself used to that for protection purposes. But this is where our program starts. We put 1 in trace A0, making RA0 an input. We put 0 in trace C7, making a RC7 an output. We put 1 in trace D2, making a RD2 an output. We said now, in the previous example, we just said assign 0 to trace B. We're making all the bits of port B output. Here, we just want this bit in port A. That's why we say trace A bits dot trace A0. This we write if we want only 1 bit in a trace to be used. Again, here, this trace C bits means we want 1 bit in RC, sorry, in trace C. Again, here you say trace D bit, you say we want 1 bit in trace D. Now, guys, I did say this in class, and I'm saying it again. Any pin that you are going to use as outputs, it's advisable to clean those pins before your program starts running. So here I set up these pins, then I put 0 on the motor and 0 on LED1. In other words, here in this schematic, I put 0 there and 0 there. I'm switching off the motor and switching off the LED so that if the motor runs, it will be due to the instruction that I send to the microcontroller. If that LED turns on, it will be due to the instruction that I send to them. Because there can't be anything on this pin before the program starts running. To make sure that what goes out is what is from my instruction, then any pins that you are using as output, guys, I advise you to first clean them before you use them. Then let us look at our program. Now, this while one says keep on doing this. This is the while loop that these 2 brackets, so our program runs there. Then here we test with the if. Because I'm having 2 actions here in the if, then I put it in brackets. If it is 1 action, I do not put the brackets. I did explain this in class. So here, this line tests if the switch is closed. We said we use the equal sign. In other words, if on the switch we have a 0, this says if this is equal to that. That is how we test if the switch is closed, there will be 0. If there is 0 on the switch is closed, then we want the motor to run and the LED must turn off. This else means what must happen if the switch is not closed? The LED must turn on and the motor must be off. Is there any comment on that, good people? I want to demonstrate that in Proteus. If you don't have question, then I can quickly demonstrate that on Proteus. Then we talk about the test. Remember, there are activities that are always given to you at the bottom. Let's assume you guys don't have problems with that. Then let me open that program. Now, good people, I want to share the program with the switch. Or no, the schematic with the switch. I'm now sharing the schematic with the switch. Can we all see that circuit on Proteus, guys?
No. Yes.
Yes.
Okay. So again, guys, always note that we use the animated components. For the LED, we use the animated. Here I chose blue. The motor also we use the animated. If you just take a generic symbol, it will just be a symbol for the motor, it will not turn. But the animated one will behave as a real motor. Then this is a button type switch that we close and open. Before we play with this, guys, let us look at our program. This is the program that I was showing you in the lesson exactly. I first wrote it on the lesson, then copied it and pasted it here. This is the program. Okay, then let us run this now. Okay, Can you see that the LED is on there? Now, guys, this is what I want you to take note of. We said a red means 1, blue means 0. So we said we put 1 on master clear. There is a red dot on master clear. Now look here, the switch is open. We have a red dot sitting on RA0. That means if there is 1 on RA0, it means the switch is open. Look what happens on the output side. When the switch is open, we have a 1 on the LED 1, the LED is on. Can you guys see that the LED is on? I chose this color. I don't know whether it's bright enough for you to see.
Pretty clear, sir.
You can see, eh?
Yes. Yes, sir.
Okay. Now, look at the motto. Look at the motto. Now I'm closing the switch. I will close and hold. Look what is happening on the motto. Can you see? Can you see now that the LED is off and the motor is turning?
Yes. Yes.
Then I release the switch, the motor stop, the LED is on.
The motor is not turning now, sir.
Look at the switch now. The switch is open, eh? The switch is open. The LED is now on. The motor is off. Now, if I will use this to hold. Look at there, guys. The switch is closed. We've got a blue on RA0 now. That means we are applying a 0 there.
Close your mic, guys.
We have a 0 on the LED, and the motor is running. Eh? Can you see the motor is running? The LED is off. There is 0 on RA0. But if I release that, the switch is open. The motor has stopped. The LED is on. So here, guys, I was demonstrating to you that this is how we read the switch. For your application, guys, not in this test, I will explain that in detail as we go on. For tests and for exam purposes, you must be able to work with up to 3 switches. I demonstrated with 1, and I gave you a task to test the other switches. But for this test that we are going to write with you, will only be tested on 1 switch. You need to practice this. Any question on this, guys, before we talk about the test? I think I've spoken too much. I said more than I wanted to say. Any question on the switch?
Sir.
Yes.
Ngicela ungiphinde ungichazela la ku-red no-blue angisazwanga kahle lapho ukuthi off kanjani switch.
Okay. Now, look carefully here, guys, on the screen. A red dot represents a 1. A blue dot represents a 0. So look here, this blue dot is that ground. Now, with the switch open, we have a 1 sitting on RA0. From this pull-up resistor, we said this is pull-up resistor because it pulls this pin to logic level 1 when the switch is open. Allow me to stop this and look at the program. I want to show you something. Here on the program, if you look on the program here, we say if the switch is closed, we will put 1 on the motor and put 0 on the LED. If the switch is open, this is on the output side now. This is switch closed, that is on the input side. What do we do on the output? We put 1 on the motor and 0 on the LED if the switch is closed. But if the switch is open, there is 1 on the LED and 0 on the switch. Let us look at our schematic now. The switch is open. If the switch is open, we have a 1 on our input pin. But on the output side, we have got a 1 on the LED and a 0 on the motor. Now, if we close this switch now, we've got a 0 on the pin. There was a 1 there from the pull-up resistor, But if we close the switch, there is 0 on the pin. Also, we've put 0 on the motor. Because this is magnetic, guys, the resistance there is very low. That is why we don't see that, but we have put a 1 here. And we've got a 0 on this side. There's 1 on the side of the motor and a 0 coming from the ground. Look, the ground is putting 0 on the cathode and putting 0 there. So this one here is turning our motor and a 0 on the LED. But if we open the switch, we have a 1 on the LED and a 0 on the motor. Because the motor is not turning, we can see that 0 on. So guys, this is the logic that I want you to understand to be able to master what we are talking about. Now I want to talk about the test. I just want to ask if there's anybody that still has a question on what we have done. We have covered almost everything that we have done with you tonight. And yes, I did a demonstration. Sorry?
Yeah, bengicela ukubuza ukuthi la ku VDD yabo i-connection is just one resistor le. Ayikho isivele isidingo sokuthi ufake the parallel connection yabo 10K laba ku.
Okay, that's a good question. Guys, if you build the circuit with a physical microcontroller, we advised like I showed on the schematic. Guys, let me unshare this Proteus. I will unshare Proteus and go back to lesson 4. Okay, I'm now sharing lesson 4 so that we can talk about this. If we design the circuit, guys, the advice, so the instruction was that we must connect 10K to the master clear. But when we design using Proteus, Proteus automatically connects to us. That is a simulator, nothing will be damaged on it. But on a physical microcontroller, it's advisable that you have that resistor, otherwise you are going to damage that pin. So in the really physical microcontroller, when we design and when we build, we need to connect this resistor. But on Proteus, it's just a simulator. It automatically connects for you there. You can connect a resistor, you may not, nothing will be damaged. There's just a simulation. That's what we're asking me, sir.
Oh.
Yeah, nothing will be damaged there. Okay. But for the physical, when you do your design, then you must connect to that. We may give you the components before the end of the semester and expect you to build a circuit, and you must connect that resistor. Guys, allow me to talk about the test now. I will unshare this lesson 4. Then I want us to talk about the test. Then we'll come to conclusion. Okay. Now, good people, I'm sharing this document. I hope we can all see. So our test paper will be like this, guys. Please do not write anything on this circle. That is where I write your score. So you are divided into different groups. We had people complaining that they did not get their scripts back and so on because we were putting them outside in the previously. But this time, guys, after or when we come back, after writing the test, I want to bring your script to your group, then you can collect your script there. What is left, then we put it outside. I don't have a space inside my office to keep your script, guys. But I want to first bring them to class and you take your script so that you don't lose it. So we are divided into groups, week 1 day, week 2 day, evening group A and evening group B. I request that you put a cross on one of these boxes. If you are in week 1 day, put a cross here so that I can bring your script when it's your time to come to class. If you're in week 2 day, put the box here so that also you can bring your script there. but you can make arrangements that you come and check your scripts if it's not your turn to come to class. Then if you are in evening group A, also put a cross on there. If you're in evening group B, put a cross there. Then here, guys, on the name, do not write your name. We want the surname and the initials. Some just write the name and leave it like that. Then it's difficult now to record the results. We have to record the results. The system indicates the surname and the initials, and we want you to do the same. Please write surname and the initials. Here, write your student number and the sign below here. Says one good people. Then the test then here, I did not put the date, but we know it's next week, Tuesday is test 1. This is a code for digital systems 3-party. There are others that are in different codes. That is not a problem. We pick that up in a system. But generally, this is the subject code. Okay. Then, guys, I've got this instruction here. It says, write your name. Maybe I should change this and say surname and initials and registration number. For the future, guys, I'll change that and take out name. Here, we are expected to answer all questions. You write it directly on the question paper. You can write it in front and at the back of the paper. Says one. Then if there is a need to draw a diagram, you can draw it freehand. You don't need to worry borrowing the ruler if you don't have. You can draw it freehand, just that it must be neat. And I advise that you draw your diagrams in ink, although people use the pencil. I've noticed that you guys lose time or waste time in most cases, that you first write in pencil, then erase and write on ink, or write ink on top and erase, and sometimes do not erase. So it means you need to double the time that you are going to take to first write in pencil, then write in ink. I don't know why you do that. First time to see that. So your test, guys, will be 1 hour and 50 marks. Okay. So at the bottom, then, guys, I put this. This is where I put the marks for each question. You do not worry about signing there. It says for examiners use only. Then, guys, this is what to expect. I know some of you were thinking that this is a test paper. Now, this is what we have done, and this is what you will be tested on. Where the important registers that we have discussed with you is the port, the trace, and status. Guys, you need to know these registers as you know yourself. Know what the port is used for, what the trace is used for, what is the status is used for. Know the bits in the status. Know how they are affected when you are doing arithmetic or logic operation. Then you must be able to display something on the port. It can be the whole port or a pin, just like I've been demonstrating to you now. So you need to know how to send something on the port or send something on the pin. It can be the whole port or the pin, just like we have done. You must be able to use the for loop to count. I've just shown you the for loop, and we were counting and displaying it. Or on port B, you saw the countdown there. Exactly what I demonstrated to you. Then you must be able to flash LEDs. You must be able to toggle LEDs. You can flash one LED, or you can flash all LEDs, or you can toggle. If you toggle, we mean the alternate ones are on and off, either the nibbles or the bits or the pairs. Then you need to know the data types. Then you need to know the C language instruction. Here on C language instruction, say you must be able to write an instruction that makes a bit an input, or makes a bit an output, or make the whole port output, or the whole port input, or that it turns on a pin, or turns off a pin, or turns off all bits, or turns on all bits, and so on. Then you must know the C language functions. We've got the main function, then we can have other functions. Then we said the function can have an input or output, or the function can have no input and no output. That's how we say void and void. But I gave you an example when we're using delay of a function that has an input but no output. So we've not done examples with the output with you. So you need to know the example of a function with input, a function with no input, a function with no output. Then you must be able to write a program in C language. Then here, guys, you must be able to compare two quantities that we call comparison. For example, I can give you two programs. I'm just making an example. I don't mean I will do that. But if I give you two programs and say, compare these two programs, you need to look at what the first program is doing and what the second program is doing. Then we can say this program is doing this program is doing that, therefore they're doing the same thing or they're doing different things. CS1? But you must be able to compare two quantities. Then I can give you a program with errors and say, identify what is the error in the program. Or I can tell you that if you run this program, it's not doing what is expected. What is the error? So you need to know, guys, concentrate on the programs that we have done together. Do not go outside of what we have done together. Then you must be able to develop a system. Here, develop a system, guys, I can say develop a system, I can say design a system or whatever. But again, your system, make sure that you can be able to sketch all the diagrams that I've given you in class and the lessons that we have done so far. Then you will keep on expanding on that. But I do not like giving people something that we have not done together. So make sure that what we have done with you, you know it as you know yourself. Guys, this is what I wanted to cover with you. Now, if it's okay with you, allow me to stop the recording, then I will open the floor for everybody to make any comment or ask any question. Okay, I've stopped the recording then, good people. Yes, miss?
Sacaubuza wagcina uthe kuma-email esibhala ngomhla 13 asimanje ade uthi sibhala ngomhla 12 noma mhlawumbe usebenze imistake yini.
Sibhala ngolesithathu.
Okay, siyabonga.
Sibhala ngolesithathu, guys, then usungacheka kwicala. Guys, it's open period now. I've stopped the recording. I don't know whether what I've covered with you here helped you in any way, but if you still have problems, you are free to ask. If you have a question, you can bring it up, or I will still be available until you write. You can also come to me. Is there any comment? Yes. Yes, Telcom.
Yes, sir. I want to know where are we going to access this class?
Sorry?
Where are we going to access this class because we are guests here?
Oh, lolo.
But you can download the
anyway, guys, when we finish here, this will be available. I will post it on Blackboard.
That's not a problem, sir.
Okay.
One last time, sir, the function of a status register. Can you function of it? Status register.
Okay, guys, allow me to share this document here. And share that. Then let me share this. This is the data sheet. So guys, on the data sheet that I gave you, I minimized that. Let me enlarge it. I will zoom it 220% then. Okay. Guys, if there is anything that you wanted to check in here, you can check, scroll on the what you call the menu here on the left hand side, or you can go to the top there and say find. I want us to find the status register, so I'll just type the status there. Then we can scroll through here. It says not found. How can it be? Oh, I wrote it. That is not a status. The status there will be a. Okay, it shows it in memory and all that, but I want us to find the description of a status register. Here is where it is explained, good people. That is section 4.13. You will notice that in the lesson, there's a lesson where I said, read chapter 4 in the data sheet. So when you read chapter 4, part of it we are going to come here. Oh, sorry guys, when I click here, I must switch off this Zoom. It means I'm on automatic Zoom there. Okay. Well, I will not click on this straight now. I'll just use the arrow on this side. I'll check why it is on automatic zoom. Okay, it was 4.13. Oh, I can quickly come here, click here, then go to 4.13, the status register. Here it is. So here, guys, they explain everything about the status register and what it does and how to use it. Then they explain each bit. Here is the explanation. So guys, I will expect you, just like I said, that you must read chapter 4 in the notes when we're talking about this. I will expect you to read here to find all the answers about the status register. They explain the Z, the DC, the C, the OV, and the N, and they give you this diagram. Another thing that I did not explain to you guys in class, if on the register here, if they write R, that means you can read on that bit, /W, it means you can write on that bit. This .X, it means this bit can be any value before your program starts running. Our X then, guys, can be 0 or 1. So it means that before you test, you must always make sure that you reset the bit. This dash means these bits are not implemented, and this 0 meaning it must be taken as 0. So if you write to the status register, you must make these bits 0. That is what the instruction tells us. But here they explain. Here, up here, they will explain what the status register is. You say it can be the destination for any as with and all that, but this is what it has, says Z, DC, OV, and so on. Then we write it to these bits. They explain everything. But for us, guys, we want to see what this bit means in a making example. And if I perform some arithmetic, which bit will be affected? Guys, if you say which bit is affected, it's not enough to say the N bit will be affected. You must say that if this happens, this bit will be 1. What you want is that it will be 1. For example, N will be 1 if the result is negative. OV will be 1 if there is an overflow to the sign bit. Z will be 1 if the result is 0, and so on and so on. Do not just say that the N bit will be affected. State which bit will be affected and how. What will it be at the end of the operation? So guys, I will expect you to read this section on the data sheet. Also in the book it is explained, but I'm more interested in the data sheet. So you will find the answer to that. Before we close, guys, allow me to share the book. There's something that I want to show you in section 7.1 in the book. This is the book. Now, my problem is that if I click on the book, it does not auto zoom. Something is wrong there. Okay, I'm sharing the book now. I want us to go to chapter 7, then I'll give you a chance to ask your questions. This is chapter 7. This is where our C language work starts, guys, but we'll do everything else. Now, this is what I want to know. This section here says the following are some of major reasons for writing program in C instead of assembly. It's easier and less time consuming to write in C. Guys, it's easy to write a program in C. It does not mean that the C language is easier than assembly. Say C is easy to modify and update. But for me, for those that are experienced, it's equally easy to write in assembly. But this is what I say. You can use the code available in function libraries. Then that is now what it is there. You get the libraries from the compiler, then you can use them easily, easier than in assembly language. So C code is portable to other microcontrollers. This is what we're explaining when we're reading on the notes pages 2 to page 11. So these are the reasons that are put for C. But for test and for this test, guys, we are not expected to know this theory. We'll come back to this and polish it up properly and then tell you what you need to know for the next test or for the exam. But for this test that is coming, guys, stick to what we've done up to now and to what I told you this evening. Okay, good people. Any other comment? We have come to the end of the road now. Yes, Leland. Sanzo, who is it?
Overflow lapho ufaka khona ama-cross uzofaka u-evening ku-group B. Sengisho sima ku-overflow thina.
We've got overflow ka-day, overflow ka-B. In theory, we all come, the overflow works in the labs. So I will bring the scripts in class. Mau overflow ka week 1, just type week 1 day. Mau overflow ka week 2, just cross week 2 day. Then I will bring your script there.
I saw.
Okay. Good people, this is what I wanted to cover with you. But ngivulelekile ma ikhona ufuna ukukhuluma engakhulumi. Ma ukhona osedelile seningahamba noshaya imovite and get ready for Wednesday.
Ayikho imovite so imali ayingenanga.
Wow, sorry about that. Utheni uMaview?
It's uNasFast ukhokhe ngolwesihlanu. uMaview akasekho esikoleni.
Ololo. Sorry. Hayi ngoba ngihleka ngiyanizwela. But it's good. It means you'll stay indoors over the weekend and prepare for your test, eh?
Sorry, sir. Before uhambe.
Yeah.
Would say for notes asifunda chapter 4.
4?
For i-part notes isifunda chapter 4.
I-part note.
I-notes.
We statusless here. Guys, on the lessons, look at the lesson. At the beginning of the lesson, I indicate where to read for each lesson. That is what you need to check. I tell you where to read in notes, where to read in the book, where to read in the data sheet. Those are the sections. But do not read everything. When you go to the book, on the section that I refer you to, look what we have done and polish up on that. Okay, good people. Have a good evening.
Thank you.
Bye-bye, sir.
Bye.
Kodwa siyawusaveza ngisho question manje.
Miss?
Kodwa siyaveza ngisho question manje ngephutha.
It's unfortunate. I-test ayikho kule computer, guys. I only copied what I showed you.
Siyabonga, hayibo.
Sengilindele kangaka nje ngase nga-screen record ngithi kuzovela question 1 lutho.
Sorry, next time, eh?
Usachazwa ukuthi unomgula thizeni nje.
Ayenzani boy. Wasn't